When giants collide, Newton versus Maxwell, Einstein's mental battle pitted two intellectual giants against each other in the most fundamental way possible. Isaac Newton had established that all velocities are relative, never absolute, requiring the phrase with respect to for any meaningful measurement. James Clerk Maxwell had discovered that light travels at exactly 299,792,458 meters per second, according to his electromagnetic equations, maintaining this speed regardless of the observer's motion. These discoveries seemed to contradict each other at the most basic level, creating a puzzle that would torment Einstein for years. Newton's breakthrough had proven that every measurement of speed depends entirely on the chosen reference frame. A car driving at 60 miles per hour moves at only 20 miles per hour with respect to another car traveling 40 miles per hour in the same direction. This relativity extends throughout the cosmos. The International Space Station orbits Earth at 17,500 miles per hour with respect to the planet's surface, yet Earth itself hurtles through space at 67,000 miles per hour with respect to the Sun. The Sun races through the Milky Way galaxy at 514,000 miles per hour with respect to the galactic center. Newton's laws insisted that no single reference frame possessed special status, and motion could only be described in terms of relationships between objects. Maxwell's electromagnetic theory presented a completely different picture. Through mathematical analysis of electric and magnetic fields, Maxwell determined that electromagnetic waves, including light, propagate at a fixed speed through space. The speed appeared universal, unchanging, and absolute. Unlike the relative velocities Newton described, light seemed to maintain its precise pace regardless of who measured it or how they moved through space. A scientist standing motionless would measure light at this exact speed. An astronaut racing through space in the opposite direction would measure exactly the same speed. The contradiction struck at the heart of physics. If Newton's laws truly govern all motion in the universe, then light should obey the same rules as trains, cars, and spacecraft. The speed of light should vary depending on the observer's reference frame. A person moving toward a light source should measure a faster speed, while someone moving away should measure a slower speed. Yet Maxwell's equations revealed no such variation. Light maintained its constant speed in every measurement, under every condition, from every possible reference frame. Modern precision instruments have confirmed Maxwell's predictions with extraordinary accuracy. The current definition of the meter itself derives from the speed of light, fixing it at exactly 299,792,458 meters per second by international agreement. Laser interferometry systems can measure light speed variations smaller than 1 part in a trillion, yet no variation has ever been detected. Atomic clocks depend on light, maintaining its exact speed regardless of Earth's rotation, orbital motion, or the movement of measuring equipment. Particle accelerator experiments reveal the same paradox. Scientists accelerate subatomic particles to velocities approaching light speed, then measure the speed of photons emitted by these racing particles. Newton's laws predict that photons emitted in the forward direction should travel faster than the standard light speed, while photons emitted backward should travel slower. The particles act as moving light sources, and their velocity should add to or subtract from the photon's speed. Yet every measurement confirms that all photons travel at exactly 299,792,458 meters per second, regardless of the source particle's velocity or direction of emission. This creates an impossible situation for traditional physics. High-energy particles racing through accelerator tunnels should behave like speeding trains, adding their velocity to anything they emit. When a person throws a ball forward from a moving train, the ball's speed equals the throw velocity plus the train's velocity with respect to the ground. When particles emit light while traveling at tremendous speeds, the same principle should apply. The photon should inherit some of the particle's velocity, creating measurable deviations in light speed. The complete absence of such deviations contradicts everything Newton's laws predict about relative motion. Einstein faced an impossible choice between two pillars of physics. Either Newton was fundamentally wrong about the relative nature of all velocities, or Maxwell was fundamentally wrong about light speed being constant. Abandoning Newton's laws would destroy the foundation of mechanics, making it impossible to predict the motion of planets, projectiles, or any moving object. Abandoning Maxwell's laws would eliminate the theoretical basis for electricity, magnetism, and electromagnetic waves, including light itself. Both frameworks had been tested countless times and formed the bedrock of scientific understanding. Yet one of them had to be wrong, or something else entirely had to give way. The conflict between relative motion and absolute light speed created a logical contradiction that traditional physics could not resolve. Einstein realized that solving this puzzle would require abandoning one of humanity's most basic assumptions about the nature of reality itself. The answer would demand accepting something far stranger than either Newton or Maxwell had ever imagined. To expose the deeper implications of this conflict, Einstein would need to construct another thought experiment that would reveal just how profound the consequences truly were. The lightning strike paradox. Einstein constructed his famous train and embankment thought experiment to expose this fundamental conflict. He positioned himself at the center of a train platform, equidistant from both ends. Two lightning bolts struck simultaneously at the platform's opposite extremes, creating brilliant flashes that illuminated the entire station. Einstein's perfect positioning ensured that light from both strikes traveled identical distances to reach him. The beams arrived at his location at precisely the same moment, confirming that the lightning strikes had occurred simultaneously. The light from each strike covered exactly the same speed, reaching Einstein's eyes together. This simultaneity seemed obvious and absolute. Both lightning bolts had struck at the same instant, creating two events that occurred in perfect synchronization. Einstein could measure the time interval between the strikes as 0,